Next question. We're looking for atoms of uranium, and they give us a mass. And they give us a mass, if you remember what this is micrograms. Okay, so if we go back to our graphic, we can change grams to moles, right? But what are we looking for? We're not looking for moles, we're looking for atoms, okay? So I want to go from micrograms to atoms. So if I look at my graphic, I can't go from micrograms to atoms. I have to go from grams to moles to atoms. So that means I have to change the micrograms to grams. And then how do we do that? We use the prefixes from the metric system that we learned. Okay? So the metric system is going to give us a conversion factor to change micrograms to grams. And then to go from grams to moles, right? We follow the bottom arrow, so we're going to be dividing by the molar mass. So we're going to use the molar mass to change from grams to moles, and then to go to moles to atoms. Since uranium is an element, we're going to be going to atoms. So we're going to use Avogadro's number. And specifically, we're following the bottom arrow, we're going to be multiplying by Avogadro's number. So we use Avogadro's number to change our moles to atoms. So now, it's not just a simple one-step problem. Now it's a three-step problem. So to go from micrograms to grams, we have to know how many micrograms are in a gram. Well, if you remember that the prefix micro means 1/1,000,000th of a gram. So 1 microgram is equal to 10 to the negative 6 grams. And if we flip that around, 1 gram is equal to 1,000,000 micrograms. Now, our molar mass, that's going to allow us to change from grams to moles, that's on the periodic table because it's an element. We can just look that up on the periodic table. We get 1 mole of uranium is equal to 238 0.029 grams of uranium. So remember, it was grams per mole, but I went ahead and just wrote it as a conversion factor. 1 mole is this many grams, because that's the definition of molar mass. It's that many grams in 1 mole. So that allows us to change it to moles. Then we need a conversion factor for Avogadro's number. Well, Avogadro's number, remember, is the number of particles in a mole. So it's that many atoms in 1 mole. So 1 mole of uranium is equal to 6.022 times 10 to the 23rd atoms of uranium. Now, if the substance we were using was a molecule, was a compound, then our particles would be either molecules or formula units, right? We can't just, it's not always going to be atoms when we're looking for atoms. It might have to be molecules, and then we have to change it to something else, okay? But this is atoms because uranium is an element. So now what we're going to do is plug it in. We start with our 1.000 micrograms. And then there's 1,000,000 micrograms in 1 gram. And remember, 10 to the 6 is 1,000,000. And then that's going to cancel out micrograms. Since we have grams on top, we want the grams part of our molar mass, because this is basically, I'm using this conversion factor, number 1 for the first step. My molar mass conversion factor, that's step number 2. I'm using this one. And then Avogadro's number, that's step number 3. I'm using this one. Okay? So since we're trying to change it from grams to moles, right? We're going to use that second conversion factor. So since I have grams on top, I want grams on the bottom. So 238.029. We want grams on the bottom so that it'll cancel out the grams that are on top. And that's equal to 1 mole. So I put my 1 mole on the top. Grams cancel out. And if I stop right there, I would be in moles. But we want atoms. So we have to use the third step, that third conversion factor, which contains Avogadro's number. Now, since we have moles on top, we have to put moles on the bottom, right? And that means Avogadro's number goes on top. And in this situation, the particles are atoms because uranium is an element. So then your moles cancel out. And then all we have to do is calculate that. So remember, any number that's written above the line, we're multiplying by that number. And then any number that's below the line, we're dividing by that number. So since the number that we're starting with, we always put that in the calculator first. And what other numbers are above the line, we multiply by. Any numbers below the line, we divide by. So we take 1.000 times Avogadro's number, 6.022 times 10 to the 23rd, divided by 10 to the 6th, then divided by 238.029. And then when we do that, we get 2.52994 times 10 to the 15th atoms of uranium. Then we go back. 1.00 has 4 significant figures. This conversion factor here has an infinite number of significant figures because that's an exact number, right? That's by definition that there's that many micrograms in a gram. Your molar mass, that has 6 significant figures, and then Avogadro's number has 4 significant figures. So that means our least number of significant figures is 4. So we're rounding to 4. We count over 4. 1, 2, 3, 4. I marked that 9 as the 4th significant figure. The next digit is a 9. That means that 9 rounds up to a 10. Right? Or you can think of as that 29 rounds up to a 30. And so we end up with 2.530 times 10 to the 15th. Okay? We got to have that 0 to show that there's 4 significant figures. You can't drop that 0 off. And that's atoms of uranium. In this problem, we're going from silver atoms, we're going from atoms to grams. So if we go to our graphic, right, here's atoms over here. Okay, we can't go from atoms straight to grams. We have to go to moles first. So we have to go from atoms to moles, and then from moles to grams. So both times we're following the top arrow. So we're going to divide by Avogadro's number, and then we're going to multiply by the molar mass. So to go from atoms to moles, we're using Avogadro's number, and then going from moles to grams, we're going to use the molar mass. So in our first step, Avogadro's number is the number of particles in 1 mole. Since silver is an element, its particles are atoms. So 1 mole of silver is equal to 6.022 times 10 to the 23rd atoms of silver. Okay, it's atoms because silver is an element. Then our next step, going from moles to grams, that's going to be our second conversion factor. That one, since it's an element again, we can just look that up on the periodic table. The atomic mass for silver is 107 0.8682. So if we just take that number and put on it grams, units of grams per mole, that makes it a molar mass. And then when we rewrite that as a conversion factor, that's the mass of 1 mole. So we can write it as 1 mole of silver is equal to that many grams of silver. So that's our second conversion factor. So then we're going to start with the number we're given. And since we're starting with atoms, we have atoms on top, that means we want atoms on the bottom. So even if we didn't know the order of our conversion factors, the only conversion factor that has atoms in it is the one using Avogadro's number. So we're going to put Avogadro's number on the bottom. So that the units of atoms will cancel out. And Avogadro's number is equal to 1 mole. So the atoms cancel out. And then to change it from moles to grams, we're going to be using the molar mass. Since we have moles on top, now we want to put the mole part on the bottom so that it'll cancel. So we put our 1 mole on the bottom. We put our 107.8682 grams of silver on top. Moles cancel out. Then all we have to do is calculate it. We take 2.80 times 10 to the 22nd times 107.8682, because it's on top, we're multiplying by it, then divided by 6.022 times 10 to the 23rd. Remember that when you're dividing by Avogadro's number, if you don't use the little EE key, then you have to put it in parentheses when you divide by it to get the correct answer. Okay. So when we plug that in our calculator, we get our answer as 5.01545 and a bunch of other digits, grams. And if we go back and look, 2.80 has 3 significant figures. 6.022 has 4 significant figures. And then 107.8682 has 7 significant figures. So we want to go with the least number, which is 3. So we're rounding to 3. Count over 3 places, starting with the first non-zero number. So we count over 1, 2, 3, and then that's going to be our last significant figure. We look at the next number to see whether we round up or round down. The next number is a 5, so that 1 rounds up to a 2. So we get 5.02 grams of silver. Last problem. If chlorine gas has a density of 3.214 grams per liter, how many chlorine molecules are in 250 milliliters of chlorine gas? And how many atoms? Okay, so we're trying to go from 250 milliliters to molecules. So how in the world are we going to do that? Well, we have to look to see what they give us. They give us density. If you remember, density is equal to the mass divided by the volume. And if we rearrange that equation, the volume, if we rearrange the equation, the mass is equal to the density times the volume. And so if we remember back on our little chart, okay, remember that grams is mass. So they don't give us anything from our chart, but they give us a way to calculate grams. So that's what we're going to have to do. So essentially what we're going to do is we're going to start with milliliters, right? And because our density is in grams per liter, we have to change those liters to liters, or those milliliters to liters, right? Using the metric system. And then we're going to change our liters to grams using density. And that's back in probably chapter 1. We learned how to do that. So we're throwing in some old material in with some new material. So once we get it to grams, then it's just like what we've been doing. What are we looking for? We're looking for molecules. So we have to go from grams to moles using molar mass, and then moles to molecules using Avogadro's number. And that'll get us question number 1. There's 2 questions here. So grams to moles using molar mass, and then moles to molecules using Avogadro's number. That'll give us molecules of chlorine, which is Cl2. Remember, chlorine is diatomic, right? So chlorine is Cl2. Chlorine atoms is just Cl. So we got to find the molecules, and then we got to figure out how many chlorine atoms are in those molecules. Well, that's basically how many, atoms of this element are in this molecule of a compound. It's the same principle. We're going to use the subscript to do that. So go back, look, we're basically going from moles of the compound, or it could be molecules of a compound. Okay, in this case, it's technically not a compound; it's an element. But to go from molecules to atoms of an element in that molecule, we can use a subscript to do that. So we're going to use our subscripts to do that. Okay? So milliliters to liters, that's going to be step number 1. Okay? If you don't remember, 1 liter is equal to 1,000 milliliters. So that prefix milli literally means 1,000th of something. And then to go from liters to grams, we're going to use our density. So because our density is in grams per liter, that's a fractional unit, we can write it as a conversion factor. We don't have to mess around with the formula for density. We can just turn that into a conversion factor and use it exactly the way it is and convert our liters to grams. So we know that there are 3.214 grams per every 1 liter. So that's equal to 1 liter. So 3.214 grams per liter. It's that many grams in 1 liter. So that's going to be our second step. Our third step, change grams to moles, we're going to be using the molar mass. So we could look that one up on Google, or we can just take the molar mass of chlorine and multiply it by 2, because the formula for chlorine is Cl2. And we get that 1 mole of Cl2 is equal to 70.9054 grams of Cl2. So that'll get us moles of Cl2. Then, because we're looking for molecules of Cl2, the next step is to use Avogadro's number to change it from moles to molecules. So 1 mole of Cl2 is equal to 6.022 times 10 to the 23rd molecules of Cl2. And then that'll answer the first question. So we'll solve it to there, get our answer. Then we'll add the 5th step to answer the second question. So the 5th step, how do we change molecules of Cl2 to atoms of just Cl? We're going to use the subscripts. So I know that 1 molecule, for every 1 molecule of Cl2, because there's a subscript 2 there are 2 atoms of Cl. And so I can throw that on the end of my calculation, basically multiply it by 2, and then you get your answer to the second question. Okay, so we're going to start. They gave us two numbers, okay, but we have to start with milliliters. Okay, this is what's telling us. Our plan is basically tells us where to start. Okay, most of the time you just start with the number you're given. This time you have to figure out which number you have to start with. So we're going to start with the milliliters. So we'll start with our 250.00 milliliters. Then I'll put in the first, since milliliters on top, I need milliliters on the bottom. So I put the 1,000 milliliters on the bottom, 1 liter on the top. Milliliters cancels out. That's step number one. Step number two, we're using our density. Since liters is on top, I want liters on the bottom. So the liters part is 1 liter. Then we put the grams part on top. Liters cancels out. Right? I'm not figuring out whether I multiply, divide, or anything. I'm letting the units tell me where to put the numbers, and then where I put the numbers tells me whether I multiply or divide. Okay? So that'll give us grams, and then we're going to use our molar mass to change our grams to moles. So since I have grams on top, I want grams on the bottom. And that's equal to 1 mole. So my grams cancel out. And then we're going to use Avogadro's number to change it to molecules. So 1 mole of Cl2 is equal to 6.022 times 10 to the 23rd molecules of Cl2. So moles of Cl2 cancel. And then that answers the first question. So to solve it, 250.00 times 3.214 times 6.022 times 10 to the 23rd. Get your answer. Divided by 1,000, then divided by 70.9054. And we get our answer as 6.82413 times 10 to the 21st molecules of Cl2. Rounded to 4 significant figures because our density has 4 sig figs, our Avogadro's number has 4, the 250 has 5 sig figs, and then our molar mass has 6 significant figures. So we're rounding to 4. So rounded to 4 significant figures, we get 6.824 times 10 to the 21st power molecules of Cl2. Now, the second question asks how many atoms. So then we throw in another conversion factor at the end, right? For every 1 molecule of Cl2, there are 2 atoms of Cl. So molecules of Cl2 cancel, and we're left with atoms of Cl. So basically we take our answer and we multiply it by 2. And so we get our answer to the second question, 1.36462 times 10 to the 22nd atoms of chlorine, and then rounded to 4. Since it's good to 4 significant figures, we're going to round at the 4. The next number is greater than 5, so that 4 rounds up to a 5. And we get our final answer as being 1.365 times 10 to the 22nd atoms of chlorine. The end.